Linear algebra is dedicated to solving simultaneous systems of equations. The word linear comes into play because we're often dealing with lines and their higher dimensional counterparts. Recall that every line in the plane can be written as ax plus by equals c. This includes vertical lines, unlike the slope-intercept formula y equals mx plus b. In order to keep things concrete, let's look at the equation 3x plus 2y equals 4. To help us graph this, we can rewrite it as y is equal to 2 minus 3 halves x. And let me just set up the axes here. We can quickly see that when x is equal to 0, y is equal to 2. So 0, 2 is a point on the line. The great thing about lines is we just need some other point on the line and we can connect them. So if x equals 2, then y equals 1. And all we have to do is draw the line between them, and that gives us the desired result. So here's 3x plus 2y equals 4. Now there are infinitely many points which satisfy this equation. We've already seen 2 of them. So for example, 0, 2, and 2, negative 1. Or we could do something weirder, like pi 2 minus 3 pi over 2. Every x value gives a corresponding y value. Now if we introduce a second equation, that makes things more interesting. Let's take 2x minus 2y equals 1, or y is equal to x minus a half for concreteness, and I'm going to plot it in blue on the line or on the graph above. Now we see that there's only one point which satisfies both equations. It's located at the intersection of these two lines, x equals 1, y equals a half. Now you're not expected to just see that this is the answer, but at least we can check that it's correct. So if I plug in x equals 1 and y equals a half into both equations, we can run the arithmetic to confirm that both equations are satisfied. The top gives us 4 and the bottom gives us 1. Thus we have two perspectives of the same problem. The first is geometric, dealing with the intersection points of lines, while the other is algebraic and involves solving for the values of x and y. Our goal is to thus generalize this to more equations and more unknowns. So, a linear equation in n variables, and let's call those variables x1 through xn, is any equation of the following form. c1x1, c2x2, cnxn is b. We call these ci terms coefficients. The xi's are called variables, and the b is called the constant term. Alright, now that's just one equation. A linear system of equations, of m equations rather, in n unknowns, consists of, well, any collection of m of these types of equations. Now, this is going to take a bit to write out, just by virtue of how many equations need to be included. But you might notice that the coefficients now have two subscripts, which I'll explain in a second. Alright, so the coefficient Cij, here the I indicates which equation this coefficient comes from, and the j indicates which variable. So if we recall our previous example, c11 is 3, c12 is 2, c21 is 2, and c22 is negative 2, and this defines a linear system of two equations and two unknowns. So there we used xy instead of x1 and x2, but it doesn't make a difference. So that defines the system itself, but now we need to talk about solutions to that system. So if our system has n unknowns, a solution is an n-tuple of numbers which satisfies every one of those equations simultaneously. If we revisit the example above, we found there that xy equals 1 1/2 was a solution. However, note that 2 negative 1 is not a solution. So if we plug 2 negative 1 into the top equation, well, it does give us the correct answer of 4. But if we plug these into the bottom equation, it gives us 6 instead of 1, which is what we were expecting, which tells us that the equation is not satisfied. And remember, both equations have to be satisfied for this to be a solution. Our focus is going to be solving these sorts of problems.